Welcome back. Let's solve another 3x3 linear system. There are a lot of options here, but notice how the third equation has only two variables, y and z. So why don't we use the first two equations, get x to eliminate, and be left with a second equation that has the two variables, y and z. I'm going to leave the first equation alone. So copy over the 2x minus 5y plus 5z equals -1. Whereas I'm going to multiply the second by -2. Which would give me -10x minus 10y minus 2z equals -26. We've got to multiply all terms on both sides by that -2. It's going to get the x's to cancel, leaving us with -15y plus 3z equals -27. That's my fourth equation. I'm going to hopefully simplify things a bit by multiplying everything in equation 4 by 1/3, which would be the same as dividing each term on both sides by 3. Well, now if I pair up, call that equation 5. Now if I pair up equations 3 and 5, I'm going to get the z's to cancel. And that'll give me -3y equals -6. So divide both sides by -3, and we've got that y is equal to -2. Sorry, they're both negative, so y is a +2. Once we've got one of the values, things should start to fall into place from there. I could plug that back into equation 3. And that's going to give me that 4 minus z is 3. Subtract the 4. -z equals -1. So z is equal to 1. Let's put both of those into equation 2. Y is 2. And z is 1. Clean up the arithmetic by the order of operations, 5 times 2, then plus the 1. We've got the x plus 11 equals 13. Subtract the 11 from both sides. And finally, we have the last variable, x equals 2. And if you want to check that in the first equation, which was 2x minus 5y plus 5z equals -1. And as an ordered triple, we're finding x is 2, y is 2, and z is 1. Well, let's see here. Plugging in for x, y, and z respectively. multiplying before we add or subtract. We're supposed to get a -1 on the left-hand side, and we do. So the order triple 221 is indeed the solution to this 3x3 linear system of equations. Be back real soon with another example.